Hi, our paper is Learning Type Annotation is Big Data Enough by Kevin Jesse, Prem Kumar T. Devanbu, and Tawfiq Ahmed at the University of California, Davis. Why type inference? Well, there's an increasing popularity of graduate type languages like TypeScript and Python 3.5 with long-term plans to support gradual typing. Gradual typing provides the benefits of static typing in an optional setting. Recently, in probabilistic type inference, complex inductive biases have been proposed with great results. This would include LambdaNet for JavaScript and TypeScript, and Typelist for Python. They define complex hypergraphs parsed from source code. So what goes into creating these complex inductive biases? Well, researchers attempt to infer what features and relationships are important for source code and relevant to the task. Complex and diverse inductive biases encourage a better representation of the source code and things important for the task at hand. This is arguably a better representation of source code than just raw tokens, as LambdaNet results have demonstrated. So this proposes two research questions for us. Does BERT-style pre-training objectives, which are state-of-the-art for a lot of NLP tasks, work for type inference? And how does it compare with models that use sophisticated inductive biases? Qualitatively, what cues does TypeBERT appear to use for its inferences, and what inferences does it make? So we pre-trained TypeBERT on a pre-trained corpus of 25,000 most starred GitHub JavaScript projects. We remove non-code entities and tokenize the corpus. We pre-trained with a masked language model objective for 200K training steps. With the self-supervised pre-training and the contextual representations that we've generated, we now adjust these representations with a fine-tuned data set. We extract from 20,000 projects, sequences of code, and their type annotations. We use 60 projects for our test set, which was sampled from the same projects that LambdaNet and OpTyper used for their evaluation to make it strictly comparable. Training set consists of over 2 million type annotations, which includes human annotations and compiler inferred annotations. TypeBERT has a fixed vocabulary of 40,000 types and an unknown type for when it knows that the type it wants to annotate exceeds that rank of 40,000 outside of its classification layer. This occurs less than 8% in our test set. So our results show that TypeBERT does very well on top 100 at 89.51% compared to LambdaNet's 66.9%. It does very well overall in top 1 accuracy, beating LambdaNet, which uses that complex inductive bias. It also does extremely well in top 5 accuracy for the top 100. So what is the PR curve and what does that mean for TypeBERT? Well, the precision here exceeds 92.7% with a confidence threshold of 90%. At a confidence threshold of 99%, our precision exceeds 98% with a recall rate of 38%. So what this means is that TypeBERT could add about 22,000 of the 58,000 annotations in the test set with 99% confidence, or at that very high precision rate. So what evidence does TypeBERT use to make type predictions? Well, convlayer is a prototype from the TensorFlow JavaScript library. Notice that TF.js core is imported as TF, and this means that types must be prefixed with TF, which TypeBERT correctly recognizes and infers. It also maintains this consistency by typing TF tensor4d throughout the entire function. In order to infer with ReLU as a Boolean, TypeBERT must take clues from the shorthand conditional ternary expression that exists in its return statement. Additionally, an array is used as the parameter for strides, which occurs in the function conv below. TypeBERT recognizes the usage of an array and the parameter strides as array. A characteristic of TypeBERT guesses is that predicted types share lexical and semantic similarities. Notice the ranking of guesses that TypeBERT probabilistically guesses, which includes similarly named and frequently used interchangeably types. Finally, TypeBERT is confident when the answer is out of its closed vocabulary and correctly annotates UNC for params. Thank you for enjoying this presentation, and I encourage you to check out our GitHub to try our type inference model. Thank you. Bye-bye.